Ronen Eldan from Microsoft Research, and we talk about a two-sided estimate for the Gaussian noise stability deficit.
All right. Thank you for the invitation and for waking up this early to hear the talk. So the first couple of minutes are going to be about explaining all the words in the title. I guess those of you who attended Joe's talk yesterday should more or less already know what it means, so I'm going to go over it rather quickly. All right, so let's try to understand what is Gaussian noise. So given two standard Gaussian random vectors, we say that they have correlation rho between them. Rho can, in general, be between -1 and 1, but here we'll only consider positive correlation. So this happens if equivalently either each coordinate of x and y, so corresponding coordinates, have a jointly bivariate Gaussian distribution with variance 1 and correlation rho. Or equivalently, you can think about it like this. X is root rho times some standard Gaussian Z1 plus root 1 over rho times another standard Gaussian, which we'll think about as noise. And y is the same, only the copy of the noise will take just an independent copy. So you can think about both of them as if rho is close to 1, then they are more or less the same thing up to some independent noise. So we'll think about y as a noised version of x. All right, what is noise stability? So given a set in Rn, the noise stability of A, so we'll denote it like that. This stability sub rho of A will just be the probability that for such x and y, both x and y are in A. Maybe it would make a little bit more sense to divide this thing by the product of probabilities that x in A and y is in A. In some sense, the stability just measures, given that a Gaussian vector is in A, what's the probability that a noised version of this vector will still be inside A? So we should think about sets which look like this, like a cloud of many little sets, as very unstable, right? Because if I know that x is in A, it says practically nothing about y. And we'll soon see which sets we should expect to be more stable or most stable. And a theorem of Borel, which Joe already mentioned, from, I think, 85, 86, states the following: hyperplanes are basically the most noise stable sets. In other words, if H is a hyperplane, having the same Gaussian measure as that of A, then the noise stability of H must be at least as big as the noise stability of A. Half space, sorry. Did I also say hyperplane, or I just... Well, Well, this is also true for half spaces, but it's not a very clever result. All right, so the best real-life example I could come up with for the application of this is the following. Say you have a large number of street cats, and you're collecting them according to some properties which they have. For example, their weight, their height, how hard they meow, and all sorts of properties which have a continuous distribution. Let's assume that they have a Gaussian distribution, and if a cat is another cat's sibling or ancestor, then we assume that each one of these genes have some correlation between them. Otherwise, they're all just independent. And I'm collecting them according to some criteria which I determine. And what I want to do is to set the criteria such that the expected number of cats I collect is 100, and I want to maximize the expected number of pairs of cats which are related by ancestry or by being siblings. What I'm going to do in order to do that is just get some hyperplane of genes. So if all the genes are independent, then I'll just take one property, the one with the biggest correlation, and just collect all the cats whose, I don't know, color is blacker than something. Okay? Should mention that no animals were injured in the making of this example.
But you can also take linear combinations of genes. Or
Yeah. So if they're all independent, then assuming the correlations are not exactly the same, I'll take the gene with the highest correlation. If they are dependent, like, okay, basically weight and height are usually dependent, then usually I'll take it, the maximizer will be some linear combination. Okay, this example is not so important. Maybe we can move on. Okay.
What here meant is that you take a threshold function, like a linear threshold function.
It will always be a linear threshold, exactly, for some linear combination of genes, of properties, right? Okay, so
Here, rho is a number, but it could be a vector because rho should be also a matrix.
yeah, so in general, rho is some matrix, but okay, if we and the Gaussians are not independent, but we can normalize it such that rho is a diagonal matrix, right? I mean, we can.
Okay, but the diagonal won't be the same, no?
Right, and this is why I take the highest value. But in this talk, we're assuming that rho is just a number, so it's just a scalar matrix. Okay, from now on. It didn't make sense for the example to say that all the rows are the same, but let's say that from now on the cats are such that all genes have the same correlation. All right, so one could hope to find, okay, maybe before I move on, I want to comment that this theorem also implies the so-called isoperimetric inequality for Gaussians. It follows from the fact that if we take the limit rho going to 1, so the noise is very, very small, and I have the set A, which looks like this, then the probability that x is in A and y is in the complement of A, well, it'll be very small when rho is close to 1, but we can consider the derivative with respect to rho. There's actually no derivative, but if we normalize by the square root, it turns out that this looks more or less like the root of 1 minus rho times the surface area of A. And when I say surface area, I don't want to do the accurate definition, but it's the Gaussian surface area. So I integrate the Gaussian density over the surface area measure of the boundary of A. So when rho is close to 1, it's pretty easy to imagine or to at least agree more or less that, well, the probability that I'll have 1 point here and 1 point outside of A is proportional to the Gaussian surface area, right? So if I take the limit at 1, I recover a result initially proven, again, by Borel and independently by Sudakov and Tsireltsen, stating that hyperplanes minimize the surface area. Now, it seems pretty natural to ask if there is some kind of stability result for this Gaussian noise stability. Now, since we're already using the word stability, let's ask if there is some robustness for this inequality, meaning that, okay, we know that hyperplanes maximize that, but can we say something about a set that almost maximizes this? So can we say that given that the deficit between these two things is rather small, maybe A looks more or less like a hyperplane in some sense. Half space. Yeah, so when I make a mistake once, I tend to make it again and again. So maybe when I say hyperplane, from now on you should understand this is half space. All right, so maybe, well, this implies that, I mean, I haven't really formulated what this is, but a reasonable formulation would imply that, well, an equality can happen here only if those sets are half spaces, and moreover, if there's almost an equality, then in some sense we should expect the set to be almost a half space. So this was initially verified by Elchanan Mossel and Joe Neiman. I will soon state their exact result. But first of all, let's think what natural metrics one could use in order to compare a set to the closest half space to it. So I guess one natural metric we could consider is just the total variation distance. Let's define for a set A, delta of A to be the minimum over all possible half spaces H prime such that the Gaussian measures of H prime and A are the same, of the Gaussian probability of the symmetric difference between A and H prime. So for a set, I look at, so if this is the set A, then I kind of try to find the half space which minimizes the measure of these things. Then I look at the Gaussian measure and the theorem of Elchanan and Joe from 2012 says the following: up to some constant that depends on the measure of A and on rho, we know that this delta taken to the power 4 is smaller or equal than the deficit. And here and always in this talk, I'm assuming that H is such that the Gaussian measure of H is equal to the Gaussian measure of H. This is almost accurate. There is some plus epsilon here, but okay. I don't want to exactly. So this is almost the exact formulation. And
is there a functional version?
well, yes. Actually, a functional version is equivalent. You can somehow go one dimension up, just add another dimension and consider the set as a level set of a function and get more or less the same thing. Now, let's go back to Borel's inequality. So since there are many experts here for applications of this, I won't state any applications. I'll just briefly say that this was initially used in the paper by Mossel, O'Donnell, and Oleszkiewicz in order to prove the discrete analog called the majority is the stablest. It also has applications for finding max cut algorithms and many other applications. This theorem actually gives robustness, a robust version for all such applications. So one example of a consequence of this theorem is a robustness for the majority is stablest theorem, meaning that in the discrete version, under the assumption of low influences, a subset of the cube that has noise stability close to the one of majority is actually close to the majority set or function. And I just want I just want to mention that another corollary of this, under some additional assumptions, is a robust version of the Gaussian isoperimetric inequality. So taking the limit rho goes to 1, and this could be done only if this constant has a nice behavior with dependence on rho. So this is based on an idea of Michel Ledoux. One can apply this thing to get a corresponding robust version for the Gaussian isoperimetric inequality, namely if you have a set whose surface area is close to the one of the corresponding half space, then the set will be close to a half space. Now, in the same, I think it was written in the paper, so they conjectured that this constant 4 can be replaced by the constant 2. We'll address this conjecture later, but before we do this, I want to try to convince you that maybe this metric is not the best metric to measure the distance between a set and the corresponding half spaces, and the reason is the following. So let's consider some half space H. And let's think about two possible perturbations of this half space. The first one is I take a little strip from here whose Gaussian measure is epsilon, and I just move it over here. So I delete this and I put a strip here of measure epsilon. So this is the first perturbation. And the second one is the following. I take the same strip, this one. I also delete it, but instead of putting it here, I put it somewhere farther away. So say at constant distance. So let's call H minus the strip H1. This will be S1. And now we take again H1, but we add, instead of S1, we add S2. Which is a strip of the same Gaussian measure, but far away. Let's say at distance 1 instead of here it would be distance of order epsilon. So this is S2, and this is the second perturbation. And
at some point it will be an half space itself.
excuse me?
At some point, if you go too far away, it will be an half space itself.
Well, almost, but
No. Exactly, at some point you cannot go further.
No, the measure is always epsilon. So it's
Yeah.
I fixed the measure to be epsilon. So
No, but at some point, and after that you cannot move. And
Yeah.
okay, I don't see why it would be.
Because even the entire half space will have measure less than epsilon.
It means what you add will become a half space.
No, but you know,
Oh, okay,
original.
okay, right.
Then you cannot move the.
But everything all together will not be a half space. This will. Now, what I claim is the following. Conditioning on the fact that x fell in S1, the probability that y fell in H1 is almost the same as the probability that y fell in H1, conditioning on x falling in the original strip which I removed. Let's call it S0. What do I mean almost? Almost up to something which is of order epsilon. Right? Because I only moved x by epsilon. On the other hand, conditioning on x falling in S2, the probability of y falling in H1 is, well, it's some constant strictly smaller than 1 times the probability that y falls in H1, conditioning on x falling in S0. So this is what I'm saying. If I compare these three things, then I claim that this is equal to this up to something of order epsilon, and on the other hand, if I compare it to this, then this is actually much smaller, so it's smaller or equal to this, some times some, even if it's times some constant, 1 plus c, c is strictly bigger than 0 and independent of epsilon. And this means that the stability of the first set, well, what is it? So it's the probability that both x and y are in H1 plus twice the probability that x is in S2. Oh, sorry, this is what. Twice the probability that x is in S1 and y is here, plus something of the order epsilon square, which is the probability that both fall in S1. So I claim that this is something like the stability of the original thing minus something of the order epsilon square. Just because I have this epsilon of, this is the probability that one of them will even fall in either S1 or S2, and if they fall in S1, I only lose an epsilon. But the stability of 2, well, this is the stability of H times something of the order at least epsilon. Now, both of these sets have the same total variation distance from H. So I can't hope, there is definitely something I'm not capturing when I'm considering only the total variation distance. So one may hope for a metric that gives us some more information, and the theorem I want to talk about is the following. If I define the following metric, so instead of delta of A, let's consider the metric epsilon of A, defined by, we take the Gaussian centroid of H. So H is just, again, any half space whose Gaussian measure is the same as that of A. And I look how far it is from the origin, and I subtract the norm of the Gaussian centroid of A. If I want those really to be centroids, I have to divide by the volume, but it doesn't matter so much here. I claim that this metric does capture the difference between these two things, right? Because it measures how much mass I moved and also how far I moved it from where it originally was. This will be order epsilon square here, and this will be order epsilon. If I look at, this is already called epsilon, but I guess it's okay. And the theorem that we get is the following. So if I consider the same deficit, it can be bounded actually from both below and above by essentially almost the same quantity. So I have here a constant depending on the measure of A and rho times epsilon of A. And here the same thing with a different constant. Unfortunately, we don't get exactly this. We get this with a logarithmic correction. So on this side, I also have, so this is times the logarithm of epsilon of A to the -1 absolute value.
So H has also to be well chosen because what is the requirement on H? He has the same measure as A?
Well, yes. That's the only, right. But if I turn H around, the distance, just the modulo of the centroid doesn't change, right? I mean, I look at the half space and I turn it.
So the mean is like that. You change your term and you turn.
Right, but I take the norm
You take the norm
of the mean. Okay?
So, but
But it's definitely natural if I have a set A to look at the H whose norm is in the same direction as that of A. So this will be the centroid of H, and this will be the centroid of A. It's not hard to see that the centroid of H is always farther away from the origin, which is, say, here. All right? And then this distance just measures how much mass and how far away I had to push it.
And if you compare, you take the W distance, Wasserstein or Kantorovich, or I don't remember which question it is, but of the restriction. So you take the restriction to H.
Yeah, so...
You take the best one, and is it related to that or not?
Well, yes, it is related, but not exactly. That's actually a very good question, but can I touch it? I actually wanted to touch it a little bit later. So I think the metric that you now mention is in some sense even better. Okay? But it's kind of harder to approach proof-wise. Okay? Okay, so it took me a bit longer than I expected to do, so that was the introductory part, and what I'll do from now on is give some ideas of the proof, mainly focusing on trying to convince you that this quantity is very natural, or not only because it captures more, but also because it appears in a very natural way relating to Gaussian noise stability. Yes?
Does that quantity epsilon actually control that quantity delta? So there's no
Oh, right. Yeah, thank you. So so two corollaries of this. So the first corollary is that this conjecture is verified up to a logarithmic term. So actually delta square of A is always smaller or equal to epsilon of A, up to some constant, I don't know, 10. So if I just plug this in, this verifies this conjecture. But basically, this inequality is an equality in this case. This is somehow the worst case. And the second corollary is, well, again, using Michel-Ledoux's methods and taking rho to 1, the dependence on rho in this constant is good enough to get a robust version of Gaussian isoperimetry. And I don't want to state the exact theorem, but basically you can imagine what kind of... I don't remember if I mentioned this. This is not the first robust version. It improves the certain result of the result of Elchanan and Joe, and there was actually another result by guys whose names I don't remember, which give another, in some senses weaker, in other senses stronger isoperimetric result. All right. So let's try to see some ideas from the proof. So first of all, if I want to look at the stability of a set A, this is equal, let's go back to the definition. It's the probability that x and y are in A. And if you remember, I could define x and y as square root of rho times some Gaussian z1 plus root 1 minus rho times an independent Gaussian. So this was x, and y was, the first term was the same, and the second was just an independent copy. So Z1, Z2, and Z3 are just independent standard Gaussians. And definitely what I can do is the following. I can take expectation over Z1 and condition on Z1 inside this probability. This obviously doesn't change anything. Now, once I conditioned on Z1, note that these two things become independent, right? So now that they are independent, what I can do is just erase one of them and put square here. Right? Now, what we do now is we take, let Wt be a standard Brownian motion. It's clear that, well, W at time rho has the distribution of square root of rho times Z1, right? And the joint distribution of W at time rho and W at time 1 is the same joint distribution as square root rho of Z1 and square root rho Z1 plus root 1 minus rho Z2. Right? Because W1 minus W rho is an independent Gaussian. So this will actually be root 1 minus rho Z2. Which means that I can go back here and say that the noise stability of A is just the probability that W1 is in A conditioned on W rho square expectation. What I did is replace this with W1 and, well, this with W rho. And therefore, it seems kind of natural to define the Doob-Martingale MT to be the probability that the Brownian motion at time 1 is in A conditioned on the filtration at time t. So if you're uncomfortable with the filtration, we condition on W at time t here. And what we get is that S rho of A, the quantity we're interested in, is just the expectation of this martingale taken at time rho square. Right? How many of you feel a little bit uncomfortable with Ito's formula?
A little? I mean,
no. How many really have no idea what? Okay.
a little or more?
I mean a little or more, yes. Yeah, that's kind of plenty of people. Okay. All right, so really briefly, so this thing is a martingale, obviously. It's a Doob martingale. Any martingale I can write as follows. So I can write mt to be the integral between 0 and t of some process sigma taken at some s, saying how fast mt is varying, times the increment of some Brownian motion. And if you're uncomfortable with this thing, just imagine it as plus minus 1 times the root of ds. Just fix ds to be very small and take here independent Bernoulli increments. And, well, this is a very, very, maybe the most basic application of Ito's formula. Just says to us, another way to write this is that the increment of mt in a short time interval is just some sigma times the increment of a Brownian motion. This can also be imagined as a Gaussian of variance ds. And if we try to think about what m at time t plus dt is equal to, m squared at times t plus dt, this will be mt plus dmt square, which is mt squared plus 2, I just opened the brackets, mt dmt. So this thing is just a martingale thing, plus now dmt times dmt, unlike in usual differentiation, since I took root of ds here, it'll just give me dt. Sigma t dt, sorry. Right? And therefore, the expectation of m at time rho is just the expectation of the integral between 0 and rho of sigma t squared dt. When I take expectation, this term just vanishes, and I'm left with this thing. So all we care about is seeing how fast this martingale varies. Right? And in order to do this, square, sorry. Yeah, I'll get exactly to the point where this center of mass appears. So, in order to do this, I want to look at mt and try to differentiate it in a smarter way. So first of all, let's note that the distribution of W1 conditioned on what happened until time t is just a normal vector centered at Wt, whose standard deviation is √1 minus t, which encourages me to define a density ft of x to be just the Gaussian density centered here with this standard deviation, so some normalizing constant times e to the minus x minus wt square over 2, 1 minus t. So this is just a family of densities beginning from the standard Gaussian. Its center moves according to a Brownian motion, and its variance shrinks. So just imagine something moving, and the time 1, it becomes a delta measure somewhere. By definition, we have that mt is just the integral over a of ft x dx. And in order to calculate how mt varies, we want to differentiate this thing, and we'll actually differentiate inside the integral. So I want to calculate dft of x. So this is easily done by Ito's formula, and I think what I'll do is I'll just skip the calculation and tell you what the result is. So it turns out that what we get here is this formula. just half a minute to give some intuition about what happens here. So we see that in a little time increment, in order to move from ft to ft plus dt, what we do is we take ft and we add to it again ft, but multiplied by some linear function, right? This is just a linear function of x with whose gradient is distributed according to some small normal variable. So basically, the process ft is just the product of many linear functions with infinitesimal gradients. And well, this kind of does make sense because if we consider the one-dimensional case, suppose that the first linear function was 1 plus some epsilon times x, and the second linear function was 1 minus some epsilon times x. So we have many 1 plus and 1 minuses which kind of cancel out, but each such cancellation gives us 1 minus epsilon square x squared. So a quadratic thing, and if we multiply many things like that, if we raise that to a high power, what we get is something like e to the minus x squared, right? So many linear functions kind of get a Gaussian density, and well, they won't all cancel each other out. The remaining terms will give us something like e to the x, right? Or some exponential thing which will just move the center of this Gaussian. So this may be a weird way to look at this simple process, but in this context at least, it seems like a rather natural way because I have 5 minutes left. Right?
3 minutes.
Okay, great. And now we get to the main point here, great? So when I take something and multiply it by a linear function, and I want to see how it varies, how this integral varies, I only care where the centroid is located. Right? The integral of something multiplied by a linear function. If I put everything in the centroid, everything will be the same. So if I want to measure how fast this thing varies, all I care is how far the centroid of A with respect to this measure is from the centroid of this measure, which is at WT. Now, at if A was a half space in the beginning, then at any point in time, well, A will definitely still be a half space. Also, if we kind of normalize back so that this thing becomes a Gaussian measure, we can always consider some change of variables, which turns this back into a standard Gaussian measure. So A will just move, but remain a half space if it started from a half space. And the point is that if I compare any set which is not a half space with the corresponding half space which has the same measure, the centroid of the half space will always be more far away. So I'll just finish with this picture. At least it's easy to agree that at time 0, if A looked like this, and I consider the corresponding half space whose center of mass is in the same direction, well, so if this is A and this is H, the centroid of H will be more far away from the origin than the centroid of A, because it's always worthwhile to take the mass located here and move it in this direction. So at least for small values of t, it's kind of clear that if I want to maximize the scale of this thing, then I want to maximize the norm of this vector, and then I want to take the set to be a half space, and in the minus half minute I have left, all I'll say is that there is some coupling argument that kind of lets me take this principle and carry it to larger times. And well, for the robustness, you need a little, like some more ideas. But the point is that if A wasn't close to a half space in the first place, all you have to do is show that it remains far from a half space for some significant amount of time, and then the process corresponding to A is kind of lagged behind a corresponding process for the half space. And I guess I'll finish here.
Questions?
In your result, do you have any control of the constant respect to the size of when a measure of the set A? You know, you have epsilon of A.
Yeah, so the I didn't really try to optimize this, but the dependence I get is something like the size of A times the size of, well, 1 minus the size of A, and this taken to some power, I don't know, 10 or something. Well, 10 at one side and minus 10 at the other, let's say. I believe that, well, up to this constant, this is the correct dependence. But I didn't really, I mean, I don't really see an application to trying to optimize this constant. Mm-hmm.
In particular, you are proving the majority stabilized. So your proof is good for proving the majority.
Well, there's to prove the majority is stablest. First of all, you need much less. So Joe showed yesterday a probably much simpler proof, but both what I did here and what Joe did yesterday lack this component of trying to understand what the low influences will give you. If you just use this idea, or basically if you just use the Gaussian stability.
I apologize.
Yeah, well, yeah, so this is exactly, yeah.
So actually my question is, so is your proof, so if we, of course it gives much, I mean we are using, it's like shooting, overshooting, but still, if we are considering your proof idea, is it like a very different proof idea from the previous proof ideas?
Yeah, it's a new proof. I mean, it seems like, it seems like a completely new type of proof. Yeah. Mm-hmm.
So how general is this? If let's say instead of a you could use it. I mean, the argument here you can take any martingale. And
right.
You have the quadratic variation, and you have the same exact argument.
Well, that's true, but somehow for this, specifically for the Gaussians, you get a process of measures which you can actually differentiate. Right? So the Ito differential of this thing turns out to be a very simple thing. Well, you could consider, so yeah.
There could be other.
You could, okay, so maybe I'll just say that there are versions of this equation where you could do, so this appears in papers related to things proving, things in different contexts, concentration of measure on convex bodies, etc. You could start from this equation where your initial density was just any given density, and this will give you some family of measures which you can also differentiate. But I don't see how to Yeah. I'm not sure what kind of result you are hoping to do with this.
I just wanted to know how general this was, but I think you made that.
Okay.
So it's even more general than linear space. Of course, linear space you can take the mean, but here, for instance, it will be the geodesic. If it was in a Riemannian setting,
yes.
you will have to
right.
replace.
So what you have to know what a linear function is, but
here you will have you have as a geodesic going from the W2 to X, and you have to take the initial vector going in this direction. I mean, what's
right.
interesting here is
Right.
really we are getting away from the Gaussian aspect and really to the Markovian.
Yes. That's yeah. I agree. Mm-hmm.
Okay, thanks. Next talk is at 20 past 10.